As the platforms are raised, the top card in the pile makes contact with the roller, and it is transferred along to the other pile. Two photoresistors are located in the center platform along with an LED array above in order to allow the program to reliably detect when the card has passed over. The camera above the first stack uses computer vision to recognize the suit and number of each card as it's being passed along to the second stack and stores the position of the card relative to others in memory. Once all the cards have been recognized, the computer executes the desired sorting algorithm. Cards are transferred back and forth between the piles, dispensing the next desired card out of the machine until no cards remain. The machine then returns to an idle state. We are particularly proud of the implementation of the hybrid stepper motor and lead screw assembly to drive the elevating platforms. With the incredible fidelity of the stepper motor and the pitch dimensions of our selected lead screw, we are able to achieve a theoretical linear travel step of 0.01 millimeters.
Introducing the Roll-On U-Bot, or Roybot for short. It has a scooper that collects tennis balls as it travels a predetermined path. After traversing the court, the Roybot will return to its home position and the balls can be collected by the user. In our prototype, the robot starts in the idle state, indicated by a yellow LED. With a button push, the robot enters the drive state, indicated by a green LED. It picks up the balls, and once it has reached the weight limit in the scooper, the Roybot displays a red LED to show that it is full. The button can then be pressed to enter the load state, where there is a flashing yellow LED. The robot will go back to the idle state after loading and will be ready to drive again.
So our DrinkBot is a remote-controlled refrigerated vending machine. It has a refrigeration module as well as a potentiometer that lets you change the speed. So from the remote control, you can drive the robot in all four directions: backwards, left, right, as well as forwards. And then after that, there's 4 possible buttons you can press to dispense a drink from 4 slots. So here is one of them. So after pressing one of the dispense buttons, the doors will open and then a drink will be dispensed that you can pick up from the basket. Aside from that, there's also a button that lets you reset the system. So this button opens the doors and retracts all the actuators so that you can restock your fridge with drinks.
The motivation of this project is to be able to control the trajectory of the ball, which in this case we wanted to rotate in a circular path. First, initially we wanted to stabilize the top plate, which we wanted to be at a 0-degree angle, and we take the distance between this plate and the top plate and we make sure that they are leveled. As you guys can see, it is almost done finishing stabilizing itself. Now that it's stabilized, we're at a 0-degree angle. The top plate is flat. If I press this button, one of them will do an offset of 90 degrees, and we'll make a circular path. As you guys can see, one of them has an offset of 90 degrees. I'm going to show it from this side.
In our system, we have 3 identical subsystems, but one we're really proud of is the actual transmission itself. So as you can see, we have our flexible shaft coupling here, but we actually manufactured our gears and machined our rods to perfectly fit our system. So our gears are laser cut, a 1-to-1 gear ratio out of plywood, and we actually 3D printed these hubs so that they would fit perfectly on this shaft. We also machined these brass rods to ensure that the wheels in the middle would be perfectly center so that they would climb up the pipe and be much more efficient. So Ryan's going to do a quick zoom in on our system, and that's the one we're most proud of. Thank you. So Kamal's going to activate our robot by pressing this button. So as you can see, it's in its climbing state, and it will hold this threshold distance from this obstacle, and it's going to go into its retreat state, where it goes back the same amount of counts as it went forward until it hit that obstacle.
So pyrovalves are used widely in the aerospace industry because they're reliable and they're relatively simple. How these valves work is when they're in the closed position, these are O-rings right here, which do not allow fluid flow past them. So the inlet cannot flow through, but when the igniter explodes, which generates gases to push the valve open, you can see fluid can flow from the inlet to the outlet right here, and fluid can flow through.
Also, if we add fluid to symbolize a propellant in a monopropellant system, the state is on. If we put the safety on, light goes off, and we cannot fire the valve. And as you can see, the valve is not leaking, it is closed. If we take the safety off, and then push the button to actually actuate the valve,
and you could see a bit of sparks come out the right side there, and now you can see pretty clearly that there's water dripping out of the valve. This does drip pretty slowly, but it'll drain the rest of the fluid here, and the piston has successfully moved inside.
As shown, the bottom limit switch has been triggered and does not allow for the table to decrease in height any further. The automatic mode is designed to promote healthy habits by intermittently switching between standing and sitting height based on the time you set through the dial.
The movement of our standing desk is powered by our transmission system, which consists of a Pololu motor, worm gear, pinion, and rack combination. As seen in the CAD, the motor drives our worm system and turns the pinion gear. This is constrained by our housing system that is mounted onto our inner tube. The rack, which is mounted onto our outer tube, interacts with the pinion gear, which then allows for the entire inner tube system to lift up and down.
Our entire transmission system is the hardware component that we are most proud of, and it is designed to be able to carry up to 300 pounds.
The top part of Icarus has a NEMA 23 stepper motor and is used to bring the solar panel to a 0-degree angle by hitting a limit switch, and then it steps down in order to get to the angle of declination that we would like. This angle is calculated using three main things: the latitude of the place we are at, the day of the year, and the hour of the day. This is another angle view of the NEMA 23 lifting the solar cell. This program begins when a button is pressed. As you can see, the arm is connected using a motor hub, and then it stops once it hits the limit switch at the top. The next part of Icarus is the drivetrain, the most impressive part. Icarus moves left or right by looking at analog inputs from two different photoresistors and moving in the direction of the one which is greater. Icarus will move straight if both photoresistors are similar in value and do not meet a certain threshold. However, if the threshold is met, Icarus will stay still and idle. Icarus can also move with all parts fully assembled. The turns are a bit less sharp due to the added weight of the NEMA 23 and the solar panel.
So this is our, for example, our low speed flight. And so in this case, the camber arm comes up and this allows for a thicker profile, which means increased drag. So for low speed flight, this is ideal. The cool thing about this state is that we can now control the tail position. So if a pilot was like, I want more lift, we can bend that downwards. Same thing for high-speed flight on this one, except now the wing profile is flattened, allowing for less drag at high speed. And again, we can keep controlling the wing. And lastly, we have our takeoff and landing mode. And so what this does is it automatically sets the tail angle to be about minus 25 degrees, and it also increases the camber arm profile. And so when you're landing or taking off, you want to maximize drag. And so
the left joystick is used for controlling the X and Y axis motion of the robot, as shown. The right joystick is used for controlling the rotation of the robot, as shown. Last is the X button for launching the solenoid to hit the billiards ball. Let's show you how to control the robot to hit the billiard ball into a pocket.
So this was the original idea. The original idea was to have this like a different kind of panel layout. And what it would do, it would be like act differently depending on if it was a shirt mode or pants or short mode. So this one would fold, and then this one would fold, this one. Eventually, it would fold on this last panel. You can see that it does actuate quite nicely now. It doesn't slip anymore. These are the sleeve bearings, 3D printed brackets, shaft collars, shaft coupling, motor, D-shaft. And then this is the final print. I made the piece. This is what the side view looks like inside Jacob's Hall. This is after we got it to work with the D-shafts. And this is the circuit.
Right under the T-slotted rail, we have a little screen that's allowing the users to control how much sugar or coffee once that looks good to you. You can click on ready and the machine will operate. The main sensors that are incorporated in this project are the limit switches sitting behind the cup and the platform, and the ones sitting at the ends of the T-slotted rail. As the platform that carries the cup moves across the T-slotted rail, it's going to hit different limit switches, and that is how the system knows where the cup is currently at. Besides the limit switches, the motor that's sitting on the left side of the T-slotted rail is the most important component that drives the whole platform across all the processes. Of course, a drink cannot be completed until you add water into it, so water pump is also one of our actuators.
Our goal for this project was to create an interactive product that would help inform and educate younger generations about problems of wealth inequality that affect the United States. We created a claw machine that extended further based on how much money was added to it. More expensive items were placed at the bottom, and basic necessities were placed at the top. We hope that this would highlight the cyclical nature of wealth inequality and poverty in the United States.
Repeatedly placing dominoes without any falling over and knocking the others down requires precision and stability. Our design process to create this machine demanded many iterations and troubleshooting, allowing us to practice and improve our engineering skills. Although this machine is not exactly a useful one, all it takes is replacing the placer with some other end effector like a robot arm or printer head to create a useful 3-axis machine. Next, the placer moves to the given position to begin the domino pattern. Once in position, the placer rotates, allowing the domino path to have corners and curves. Next, the chute drops, which will constrain the top of the domino to prevent it from falling over when placed. Finally, the pusher mechanism pushes a domino from the stack and onto the table. Once the domino is placed, the chute retracts, the placer returns to its original rotation, and the pusher mechanism retracts, loading the next domino. That's our project, and thanks for watching.
So the basic function of this is that lead screw will elevate that platform, and depending on which shelf you want, we'll drive the shelf forward, put it on the platform, and lower it down. So here we have 3 button inputs, each indicated by each LED. This first one represents a red LED and goes to the top shelf there. So when you click on that, the platform will elevate to that position. The rack and pinion, the pinion will drive the rack forward, attached to that shelf by this motor. We'll go to that platform, and once it's on the platform, it will lower down all the way so you can reach what you want. And the same mechanism goes for this middle button, which is attached to this first shelf here.
What we have here is basically an automated turntable. As you can see, we have a dial here which you can rotate to the spice you'd like to choose, and then you press a button, and there's an actuation system with electronics inside which basically turns the turntable to the spice you chose. How it works, again, there's all the electronics. There's a pulley system down here. I'll show shortly. With the dial, you chose the spice you liked, you press it. There's a motor inside with transmission system, and it rotates to the spice you like.
The device features a cleaning box that's moved vertically and horizontally along the window, and it cleans using an electric spray bottle and foam rollers. Here we see the bottom foam rollers rotating. After the push button is pressed, the box moves up until it hits the vertical limit switch. It then moves to the side until it reaches the horizontal limit switch. Then it runs the foam rollers and propellers to clean the glass. An issue that can be seen here is a poorly soldered foam roller connection, which prevented them from briefly running. On the way up, the propellers and foam rollers are turned off as it cleans only on the way down. To speed things up, I ran this clip on double speed. Once it reaches the edge of the window, it stops, and it'll restart the process if the push button is pressed again.
You can see the tool is spinning, cleaning the plate. Once it stops, that is when the pump is running. The pump is controlled by a relay and is placed in the platform below. The arm then lifts up and moves to the next plate. If the robot was waterproof, you would see the pump pumping out the water, but as we have exposed wires, we chose not to test that functionality. Once the tool shaft reaches the right location on the new plate, it lowers down and continues spinning. Again, the time that it spins while is controlled by the potentiometer on the right side. After the tool shaft stops spinning, this is when the rinsing period happens and the pump again is actuated. Finally, cleaning process is done.
Pressing the play button will actuate the device to the desired chord position. It will then wait for a strum to be detected by the audio sensor before actuating to the next position. This cycle will repeat until the user presses the play/pause button to pause the device at any time. In the pause state, the user can also press the on/off button to reset all motors back to their original position.
Each solenoid is held in the carriage to allow it to reverse the lead screw.
In order to detect if a chord is strummed, we use a frequency analyzer module. This takes in the analog signal from our sound sensor and produces 7 band frequency signals that we can use to detect if the device is strummed, even in a loud room.
The Yuki!
The Yuki!
The Yuki!
The Yuki!
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 Lift it up a little higher. The Yuki!
It even works with Baxter.
Here you can see it in action.
Go, pedal.
As you can see, we have 2 encoders used to capture the manual actuation of the bicycle. In the front, we have a encoder attached, and it meshes with the rotation of the handlebars. In the back, we have an encoder turning with the rim of the bicycle. Now we use this to capture not the exact angular position, but we translate it into its effective angular velocity, which is then translated into the power of the RC car. To make the car as controllable as possible, we made it such that there's a linear relationship between the handlebar's turning angle and the car's turning angle. Here you can see a demonstration of just the turning.
Once a position has been chosen by the user will then press the automation button in order to compare the current location of the telescope to the desired location to view the nearest object. Once the automation state button is pressed, the motors will actuate to get closer to the actual object. Once they reach close enough to the actual object, then the motors will stop and a view will be visible. And as you can see, the motor stopped and we now have a view of the moon. And this means that we are in state 3, where information on the object is printed for the user to view.
The dog is remotely controlled via Bluetooth. It can walk forward, turn left, turn right, and bark.
If the ultrasonic sensor detects that an obstacle is too close, the dog will start turning until the obstacle is no longer blocking it.
With a bit more time and effort, the functionality of the Boston Terrier can be further enhanced. It could navigate rough terrain, carry payloads to destinations, and even act as a dystopian surveillance attack robot. The possibilities are endless.
Now, you can actuate the platform by twisting and turning the remote. The role of the remote controls the lateral motion of the platform. and the pitch of the remote controls the elevation of the platform. The remote estimates its own state using its inertial measurement unit, and then transmits its state to the platform's ESP32. The platform estimates its own state using measurements from the inertial measurement unit and uses velocity feedback to compute the required actuation of the elevation and traverse motors. These signals are transmitted to the DRV-A833 motor driver, which is used to actuate the motors. When the elevation and traverse motors turn, they engage the gears on the transmission systems. This is what allows us to actuate the elevation and traverse of the system. And that concludes the brief demonstration of the actuated camera platform and its features. If you liked the video, please hit the like button and share.
Starting at the handlebar here, we have an analog Hall effect sensor to control the throttle input. We have push buttons as our digital inputs to control various states of the motor. And then we also have a pull cable for the brake. Moving down, we have bushings to connect the steering rod to the steering stem. And then moving down further, we have the main chassis of the scooter where we have all of our electronics. So here we have a 24-volt battery that powers the whole contraption, including an ESP32 through a voltage regulator. This ESP32 communicates with this motor controller down here, which itself communicates with the brushless DC hub motor that we have over here. The brake cable mentioned before comes over here and connects to this drum brake and actuates it as such.
Here we have the throttle input, and here we have our braking system. One of the features we implemented was being able to switch between different drive modes. The scooter is always in standby mode, which is indicated by the green light. By pressing the left button, you can switch into, it activates the motor and you have the ability to switch between different driving states. You start off in the comfort mode, and by pressing the right button, you switch to performance mode. And you can toggle back and forth between the two. I will now show you how our scooter rides.
Our final project is a robotic cat toy that's inspired by a Roomba. We all have spent lots of time living or playing with cats, but sometimes you don't have the time to entertain them, and they can get sad or bored. Our final project aims to address this problem by having a completely user-free cat toy that can keep cats entertained without any effort. When turned on, the robot moves forward in a straight line, encouraging the cat to chase it. What makes this robot unique is that it has a strategy for detecting collision directions, which allows it to turn away from an obstacle. Once the robot has been caught, it drops a treat for the cat, which is a method of positive reinforcement encouraging playing with the robot as well as benefiting the cat's mood.
The second state is the driving forward state. Here, the motors are engaged by push-button activation. Each motor is driven by a nominal PWM value of D equals 150. Consequently, both the ultrasonic sensor and an internal timer are activated when the button is pushed. The third state is the turn right state. The robot turns right when the readings of the ultrasonic sensor fall below the threshold of 20 centimeters. When this happens, the motors are halted and the robot sits idle with a conditional timer. For 3 seconds, the robot waits for an external input on the alarm control button. If the alarm control button is pressed in the turn right state, the robot transitions into the heightened alarm state. Here, the robot stops moving and the array of LEDs flash in a unique pattern to alert responders of the location of the survivor.
To turn this device on, we press the button for 3 seconds. The LED comes into the button and the LED strips are turned on and we're into the first state. There are a total of 6 states, and in different states, there's a different combination of LED strips. And to move on to the next state, we simply press the button and we're into the second state. And we press the button again and it turns to a different combination of strips. And until in 6th state, and in the 6th state, we are able to adjust the brightness of the LED light with the potentiometer, which is our analog input. And to move from 6th state to the 1st state, we can press the button again, and we're back into the 1st state.